Hello, so we're going to solve a matrix equation. That's the one that I'm presenting just here. And to do that, we're going to use a little bit of abstraction. So I'm going to think of this entity as A, this as B, and that one as C. Then I'm going to write the following. A times X plus B, of course, everything on matrix operations, is equal to Cx. From here, I can transform this equation into something of the following form. Ax minus Cx is equal to negative B. Now, matrix multiplication is distributive, so I can write the following as long as I keep the order. So I'm going to write this as A minus C times X, everything on the left. So that would be equal to negative B. And of course, once we have this, I will transform it into the following expression: negative 6, 4, negative 2, negative 2, by incorporating back what A, B, and C are, minus negative 2, 7, negative 5, 5, then multiply this against X and get negative 5922. Of course, I now can transform this into something that is equivalent, that looks like this, by performing the actual operations of subtraction and scalar multiplication here. So now this is negative 6 minus negative 2 on this entry, 4 minus 7 on that one, then negative 2 minus negative 5, and negative 2 minus 5, right? That multiplying X itself. And of course, now this is going to be negative 5, negative 9, negative 2, negative 2. The matrix on the right side. Well, once we have this, we can now rewrite it as a much more simple matrix equation, the one that looks like this: negative 4 and negative 3, 3, negative 7 times X is equal to negative 5, negative 9, negative 2, negative 2. And you may say, well, look, now we can think of X as a 2 by 2 matrix. This is really the only thing that this could be. Simply look at the structure, right? This is a 2 by 2. This is a 2 by 2. So whatever this is, which is an A by B, right? The inner dimensions should match, right? And the outer dimension of this matches this one, and this dimension matches this one. So it better be a 2 by 2 matrix, right? So that means that it looks kind of like this: 1, x1, 1, x1, 2, x2, 1, and x2, 2. So by performing the matrix multiplication associated with this, we obtain an equivalent augmented system, right? That looks now like this one: negative 4, negative 3, 3, negative 7. Augmented with negative 5, negative 9, negative 2, negative 2. So we proceed to a reduction process. First, negative 1/4 of R1. Now that one reduces to 1 3/4, 3, negative 7, 5/4, 9/4, negative 2, negative 2. Next operation, I have From R2, I subtract 3 times R1, now that I have my pivot here. And now I have 1, 0 on the first column, followed by 3 quarters, negative 37 quarters on the second, then 5 fourths, 9 fourths, negative 23 over 4, and negative 35 over 4. Next operation, I'm going to multiply by the reciprocal of this entry on the second row. So I have negative 4 over 37 of row number 2, and that converts the following matrix. 0, 1, then 5 fourths, 9 fourths, 23. I'm saving some computations here that you can verify. 37, 35 over 37 on that entry. And lastly, I have from R1 I subtract 3 quarters of R2, thus resulting in 1, 0, 0, 1, followed by 29 over 37, 57 over 37, and 23 over 37, lastly 35 over 37. Saying, well, if you have seen this process in the text, you may find that this is exactly the procedure that we find to compute the inverse of a matrix, right? By solving an equation of the following kind: A times X is equal to the identity, right? But this is not our case. We're actually doing a different operation, but effectively what we're doing is multiplying by the inverse to the matrix that I'm underlying here. So really what we're doing here is isolating this X. So that means that the X is exactly the matrix that we find here. So X is equal to 29 over 37, 57 over 37, 23 over 37, and 35 over 37. Okay, I hope that you like it, and take care.